Good afternoon. This is the College of Engineering Distinguished Lecture Series. We have the honor of having Phil Duffy here, who's president of Woods Hole Oceanographic Institute in Massachusetts. The title of Phil's talk is going to be an insider's view of climate science and policy. And as you're going to find out here, he comes to this from a lot of decades of experience and even some more intense experience recently in the White House. He's going to discuss some research priorities on climate change and how we're affecting the Earth's climate, which is going to be important for us all in the future, both on possibly how to mitigate, but I think more important now that we don't really have much in the way of international accord on this matter, how we're going to adapt. And climate adaptation is really where it's going to be at in the future, unless we can all of a sudden get our act together. And even despite Governor Brown's wonderful announcement, and that's fantastic, I don't know if California is only a small emitter compared to the whole world. We've got the whole world to deal with here. So as president of Woods Hole, he leads an independent scientific institution that works on the causes and effects of climate change, but of course with the emphasis on oceanography in the oceans, but including conservation, restoration, and economic development worldwide. In his recent post to his president's blog, he writes, "Extreme weather is disruptive, expensive, and dangerous. Any major change in climate is a problem, not because the new climate is necessarily worse, but because human systems, everything from agriculture to snow removal, are very finely tuned to the old one. This is a case where change is not good, as opposed to where change is good." Phil was introduced to climate change and climate science back in the 1980s by his mother, who did paleoclimate research at Brown University. He worked at Livermore for many years. He expanded his research in academia, in public service and government, and has become a national leader on climate science, including serving on IPCC. He earned his doctorate in applied physics at Stanford University in '86. He spent 2 decades at Lawrence Livermore National Laboratory, both as deputy leader in Atmospheric Science Division and senior scientist in the Physics and Life Sciences Directorate, primarily working on climate and climate science issues. In 2008, he joined the climate team, the team at Climate Central Incorporated, an East Coast organization of scientists and journalists dedicated to increasing public awareness and understanding of climate change, eventually becoming their chief scientist. He has spent 3 years in government, first in the White House Office of Science and Technology Policy, as a senior analyst in Environment and Energy Division, and then as the White House National Science and Technology Council Senior Advisor on U.S. Global Change Research Program. In both roles, he was intimately involved in international climate negotiations, domestic climate policy, and the coordination of U.S. global change research. Please join me in giving Phil Duffy a warm welcome.
Okay, thank you. Am I audible? Visible. Is anybody awake? Okay. So, well, Tony, thank you. And it's a pleasure to be here. I've enjoyed meeting a number of you over the course of the day today, and I hope to have the opportunity to meet more of you in the reception following, and also I'll be here most of the day tomorrow. So what I thought I would talk about is some aspects of the problem of climate change, including starting with a little report card showing you the latest versions of some of the basic observational indicators that we use to monitor climate change, talk about 1 or 2 impacts of climate change, both impacts that are occurring now and those that we expect to see in the future, talk about why it's urgent to address climate change now. Climate change is a problem that we really have to prevent. Once you fix it, once you get it, you're kind of stuck with it. And then I'll move on to talking about some aspects of solutions to climate change, including the widely cited goal of limiting global warming to 2 degrees. This is a so-called 2-degree target. I'll talk about some of what we know and don't know about costs associated with climate change. And finally, I want to take up the question of, is climate science necessary? And that may seem like a strange question given the importance of climate change, but a lot of people, or some people anyway, who whose opinions I respect, argue that we no longer need climate science. It's done everything that we need it to do. And I'm a climate scientist, so I'm sure it's not going to surprise you that I'm going to argue, in fact, that yes, we do still need climate science, and I'll explain why. And I'll conclude with my personal recommendations for what I think we should be doing, both in terms of policy and research. So again, to start with, I'm going to review some of the basic observational indicators that we use to monitor the progress of climate change. This is the most widely used, most widely cited indicator, though, as I'll explain in a minute, it's not really the best one, okay? So what this is what we call surface air temperatures. It's just measurements made at weather stations and measurements made by ships. This is the temperature at the lower part of the atmosphere right above the ground. We like this as an indicator because as humans we live in the lower atmosphere. And before I tell you why this is not a great indicator of climate change, let's just talk about what it shows. It shows, as you can see, warming over the last century, but not steady warming in fits and starts. And the basic reason why there's warming in fits and starts rather than steady warming is that the basic warming trend is a response to increasing greenhouse gases, but there's a lot more than that going on here. There's other human influences like particulate pollution, there's natural phenomena like volcanic eruptions, and there's also internal variability in the system. And so the rate of warming is not uniform, and you may notice that over the last 10 or 15 years, the rate of warming has been relatively slow, and the climate change denier community has made a huge deal about this. And as I'll explain in a moment, it's really a red herring issue. You may also notice that, in fact, 2014, which is the last data point on here, was in fact the warmest year on record. So why do I say that this is not a good indicator? This is not a great indicator of climate change because of the fact that if you think of climate change as an energy imbalance between the Earth and space, which is in fact exactly what it is, the Earth has been absorbing a little more energy from space than it's re-emitting, and that's why it's warming up. And if you ask, where is that excess energy going, almost none of it goes into the atmosphere. We think about 1% of this excess energy goes into the atmosphere. Almost all of it goes into the ocean, okay? So this is really, as an indicator of climate change, this is really the tail, not the dog, okay? It's not where most of the energy from greenhouse gases is going. As I said, most of it's going into the ocean. About 92–93% we think of the excess energy is going into the ocean. This is showing measurement of ocean heat content, the upper 2,000 meters of ocean going back about the last 50 years. You can see it's warming perhaps more steadily than the atmosphere. This red curve is the last several years. And in the last several decades, we have, thanks to satellites, we have much better data on at least the surface temperatures of the oceans. You know, the problem with the ocean temperature as an indicator of climate change is lack of data, and particularly in the subsurface ocean, we really don't have very good data going very far back. Now, over the last 10 years, things have really revolutionized in this respect because of autonomous observing systems, and these things are not exactly buoys because they go below the surface, but they can drop down, take data, come back up to the surface, and transmit the data back up to satellites. And so in terms of the amount of ocean data that we have now, it's night and day compared to what we had before, but we only have this new data stream for the last 10 years or so, so it will take, of course, decades before we can really develop a long record of looking at what's going on in the ocean. Okay, so the ocean is warming, and partly because ocean is warming, sea level is rising. This is sort of the long-term perspective on sea level rise. This goes back, I put this in big font, this goes back to 1880. You can see sea level rising. I think you can also see that that curve is bending up, meaning that sea level rise is accelerating, and we think that this is a genuine acceleration, not some sort of artificial instrumental artifact. You can also see, I think on this curve, that there's an additional curve the last 20 years or so, and that is satellite data, surface altimetry of the ocean, and that allows much more accurate and thorough measurements of sea level rise. This is a close-up of the last 20 years or so, and this is the period when we had satellite measurements of sea level rise. So sea level is rising at an accelerating rate. We think that roughly half of this historical recent sea level rise is due to thermal expansion, and I just showed you the warming of the oceans, and we think that about half of it is actually due to melting land ice, introduction of, so increase actually in the ocean mass, okay? And one of the bigger sources of that land ice is the Greenland Ice Sheet. And thanks again to remote sensing over the last 10 or 15 years or so, we actually have very good measurements of both the mass of the Greenland Ice Sheet and actually the volume of the Greenland Ice Sheet. This is showing you the mass of the ice sheet, and there's a seasonal cycle in it. There's melting every summer. There is summer in Greenland. There's melting every summer, so there's a seasonal cycle, but you can see an overall trend, and I think you can see that that curve is bending down, meaning that the rate of loss of the Greenland ice sheet is accelerating, okay? And something very interesting happened, I don't know what, frankly, in 2012, where you can see 2012 was a really sort of disastrous year for the Greenland ice sheet, and at the time, a lot of us thought, oh my God, the system's really imploding, but you can see it hasn't exactly recovered, but it recovered back to its prior trajectory, which was bad enough. This is sea ice, okay? And this is documenting essentially the area covered by Arctic sea ice. The red line is observed, again, Arctic sea ice area. You can see this is going down. You can see, again, it's going down at a rate that seems to be accelerating. And this gray shaded area here is a bunch of model simulations, and the message is that the Arctic sea ice is not only disappearing, but it's disappearing at a faster rate than the models project. As I mentioned, the loss of the land ice sheets contributes to sea level rise. The melting sea ice does not contribute to sea level rise. You probably understand that, but if you don't understand that, this actually came up in a House hearing that I was at last fall, and if I can do that, I'm going to play you some clips from this hearing. And Jon Stewart did a little takeoff on this, and this is the hearing. This is a witness, my boss, John Holdren, who is at the moment the president's science advisor. He also at one point was president of Woods Hole Research Center, which is a job I have now. And this necktie behind him is actually me. That's my torso. So my torso appeared on Jon Stewart, okay? So I don't know if you're going to be able to hear the audio here.
Committee on Science, Space, and Technology.
Okay, so can you hear that? Okay. Maybe if I put my microphone closer. What's that? I'll just put my microphone a little closer. Oh, okay. I think we're going to be good. Okay. So this is Steve Stockman, a Republican representative.
How long will it take for the sea level to rise 2 feet? I mean, think about it. If your ice cube melts in your glass, it doesn't overflow. It's displacement. I mean, this is some of the things that they're talking about mathematically and scientifically don't make sense.
So Jon Stewart didn't like that. So this is what he had to say about that.
Sakes, look, here, look. Here's a glass of ice water. Hey, that ice isn't making the water overflow because it's already in the water. But imagine there's a whole bunch of other ice that's not in the water. It's on the land. You know, the part where the water isn't. And then when temperatures rise and the land ice melts enough to fall in, oh, it's everywhere! It's everywhere! Do you understand?
Okay, science lessons on Comedy Central. I had actually never watched, I'm embarrassed to admit this, I had never watched Comedy Central before, but I really think Jon Stewart's great. Okay, so what I've showed you is observations indicating, clearly indicating a warming planet, right? And one of the messages I want to leave you with is that there's a lot of very rigorous science going on examining what is the cause of these observed changes, and specifically how much of these observed changes are due to human activities and specifically increase in greenhouse gases as opposed to natural factors. And there's a lingo for this, and we call it detection and attribution of climate change. And I just want to impress upon you that we don't just assume that because we think it should get warmer and it is getting warmer that the observed changes are in fact due to greenhouse gases. And this is a cover of a recent report by something called the Intergovernmental Panel on Climate Change, which some of you may be familiar with. And this yellow box here is a summary statement by them, which I guess I'll read it to you. But it's a summary statement, and it says this. It says, it is extremely likely, which in their terminology means more than 95% likely, that more than half of the observed increase in global average surface temperature from 1951 was caused by the anthropogenic, and that means human, increase in greenhouse gas concentrations and other human forcing. So this is a very quantitative, very rigorous statement saying that we think that, we're very, very confident that most of the increase in global average temperature is not natural. And in fact, the best estimate is that the warming is essentially all due to human activities. So this is focused on one climate variable, which is changes in global average temperature. This detection and attribution work has also been applied to other variables. This is a paper in the lower left on precipitation. This is actually temperature, but this is not the upper right. This is a paper, this is the first paper of its kind that looked at warming on a very regional level. This happened to be the state of California, showed that the recent warming in the state of California seems to be too rapid to be due to natural causes. And this paper on the lower left is something different, and this is trying to do detection and attribution. In other words, assigning causes not to climate change itself, but to impacts of climate change, like increases in wildfire. So let me turn now to, this I mentioned Intergovernmental Panel on Climate Change, and for those of you who don't know what it is, it's a body that is organized by the United Nations and has 195 member nations. And the main thing that they do is they put out these massive assessment reports summarizing what is known about climate science. They do this every 6 or 7 years. And these are in 3 volumes, and you can read what the 3 volumes cover. And when I say massive, I mean literally massive. The report on the left, which is the physical science basis of climate change, thank you. The report on the left, the paper version, my copy weighs 9 pounds, okay? So this is a very serious thing. And one of the things I did in the White House is me and one guy from State Department coordinated the US government review of this whole set of volumes, which is about 3,000 pages of stuff. And part of that process, I'll show you in a few minutes, is negotiating among 195 countries, is we negotiate every word of summary documents, and the summary documents are 30 or 40 pages. So I did want to mention a little bit about climate change impacts. And one of the messages that you should understand is that climate change is having impacts today, although not all those impacts are recognized. This is extreme heat. This happens to be from a paper by me. And this plot answers the following questions. And it's looking at summertime seasonal temperatures, okay? And it's addressing this question. Summertime seasonal temperatures, summertime temperatures that used to occur 5% of the time, okay? In other words, relatively rarely. How often do they occur now, okay? And if you can read the color scale, you can see that in areas of the western US, temperatures that used to occur, summer temperatures that used to occur only 5% of the time are now occurring 50, 60% of the time, okay? So this is huge increases in extreme heat. And this is documented in other ways as well. And this is another impact, and I'm only going to show you a couple because I don't want to keep you here all night, but this is an important one. This is water scarcity. And this is perhaps a bit of a complex plot, but this is showing inflow into the surface storage system, the reservoirs in California. And the thick curve here is the historical inflows. And you can see the historical inflows continue into June, July, and August after the precipitation has stopped. And what that is snowmelt, okay? And the other curves are different climate change scenarios. And what they all have in common is that they produce more river flow, more flow into the reservoirs in winter and spring, early spring, when we can't capture the water, and reduced inflows into the reservoirs in the late spring and summer, which is when we really need the water. So simply by warming, simply by shifting the timing of snowmelt and the timing of stream flows, climate change has had an impact on water scarcity in California and in the rest of the western US. And this basic story has been known for 20 years. And part of the reason I'm mentioning that is that basic message that we know that climate change has exacerbated water scarcity in California, we've known that for 20 years. That often gets obscured in some of the public discussion about the present drought. And a lot of that discussion is about the narrow question of, is the present lack of precipitation associated with climate change? Some folks think that it is, but what this slide is telling you is that absent any changes in precipitation, warming alone and the melting of the snowpack has a huge impact on, or a significant impact on water scarcity in California, and we know that, and we've known that for a long time, okay? And that's an important message. This is some work on looking at future impacts. This is some work on how climate change affects crop yields, and this is feed crops in the Central Valley. And these are two different climate scenarios, and you can see all of these curves, or most of them anyway, are going down, meaning that climate change tends to decrease crop yields. And you know, there's controversy in the public discussion about impacts of climate change on agriculture, but in the scientific community, there's wide agreement that the impacts of climate change on agriculture, by and large, are detrimental. And of course, it varies from crop to crop, it varies from region to region, but by and large, we think the impacts are detrimental. Now, this is a summary statement from IPCC, Intergovernmental Panel on Climate Change, and this was just released, actually, I guess about a year ago in spring of 2014, and I'm particularly proud of this because I played a key role in getting this language into the document. Me and one other guy, a delegate from the United Kingdom, argued strenuously for this, and this is what it says. And this is the only place in these 3,000 pages actually that discusses what if we don't meet this so-called 2-degree target, what if climate change really gets big. And I'll read you the language. It says, risks are high to very high with global mean temperature increase of 4 degrees C or more above pre-industrial, and includes severe and widespread impacts on unique and threatened systems, substantial species extinction, large risks to global and regional food security, and the combination of high temperature and humidity compromising normal human activities. It also says that the precise levels of climate change sufficient to trigger tipping points, parentheses, thresholds for abrupt and irreversible change remain uncertain. And that's an important point too, which I'll get back to. So this is some very cautionary language about what if we don't control this problem. And this is one of these, I mentioned that we negotiate these summary documents, and it's actually a crazy process. Okay? These are 40 pages of text, okay? And the way the process works is we have delegations from 195 countries. We discuss sentence by sentence, and nothing is included unless every single nation agrees, okay? And there's no method for overruling somebody who objects. So any party, any one party can block anything, okay? And so it's a crazy process of consensus building and negotiating and behind the scenes deals, and you know, it ends up going on throughout, you know, 24/7. And we spend about a week doing this for each of these volumes. And I took this picture, it was literally 4 o'clock in the morning. You can see the Japanese, this is in Japan, you can see the Japanese delegation, either they're very intently looking at their laptops or they're taking a little snooze. And this is actually when 12 hours of jet lag, this is the rest of the US delegation here and here and here. This is when 12 hours of jet lag is great because it felt like 3 o'clock in the afternoon or something. So we were actually, at that point, relatively wide awake. Okay, so here's a key message, okay? And that is climate change doesn't fix itself, or at least it doesn't fix itself on any kind of timescale that we care about, okay? And in this way, it's different from other environmental problems. Most environmental problems, if you stop the source of the problem, if you shut off the source of the problem, the system heals itself relatively quickly. Climate change doesn't work that way. CO2 stays in the atmosphere for a very long time. And these are model simulations here. This is a hypothetical case of what if we burn greenhouse gases, burn fossil fuels until the year 2100 and then stop completely, just utterly cease using greenhouse gases. What happens to temperature? Well, you can see this, if you can read the scale here, this goes out to the year 3000. You can see the global temperature goes down a little bit at first, but then really, really plateaus and stays up there for a hell of a long time. And that's just because if you put CO2 into the atmosphere, it just stays there for a very long time, okay? This is a similar sort of, this is actually sea level rise, or really the thermal expansion component of sea level rise. And here the story is even worse. Here, not only does it not get better, but it keeps on getting worse for centuries and centuries, and that's because the vertical mixing in the ocean is very, very slow. And it takes a long time for heat applied at the surface to penetrate into the deep ocean. Okay, so I want to talk now about some solutions, and I've alluded once already to the so-called 2-degree target. The 2-degree target is widely discussed in policy circles, and what it refers to is the idea that we should not let the globally average temperature increase more than 2 degrees above the natural value, okay? 2 degrees of warming. And one thing that's interesting about that target is it sounds so benign, right? 2 degrees, right? I mean, what's 2 degrees, right? It's probably 10 degrees warmer today than it was yesterday, or 5 degrees, right? Or certainly over the course of a day, we all experience temperature variations much greater than 2 degrees. So what is the big deal about global warming of 2 degrees? And it's kind of hard to wrap your mind around it, but I'll just make this point, and that is that the temperature variations that we all experience every day and from season to season are local, okay? They're not global. Increasing the global temperature by 2 degrees requires a huge amount of energy, and if you go back and look at temperature variations over centuries, global scale temperature variations, they're much, much smaller than 2 degrees. They're typically measured from century to century in tenths of a degree, okay? So 2 degrees is a really big deal. And another way to put that in context is the difference between now and an ice age is maybe 5 degrees, okay? So 2 degrees is not that. But of course, the difference between now and an ice age is like completely different planets, okay? So 2 degrees of warming is a lot, okay? And well, maybe I'll skip that because I don't want to take too much. Well, I don't want to take too much time. You can ask me about that. Okay, so this is the assessment of the Intergovernmental Panel on Climate Change of what would we have to do in terms of reducing emissions to meet this 2-degree goal. And I'll discuss in a minute, is this the right goal? I'm not sure it is the right goal, but it's the goal we have, okay? So what would it take in terms of reducing emissions? And the message from this is that it's doable, but we have to start now. And what the analyses show is that to meet this target, we would have to, by 2050, we would have to reduce global greenhouse gas emissions by about half. 40 to 70% is an uncertainty range, but we have to reduce emissions by about half. And that's bad enough, but that's reducing emissions relative to today's emissions, okay? And what this is saying here is that, in fact, if we don't have climate policy because the population of the world is increasing, because economic activity is increasing, absent climate policy, those emissions would actually go up substantially, okay? So we would have to reduce more than 50% relative to some business as usual scenario. And by the end of the century, we have to cease global greenhouse gas emissions entirely. In other words, we have to completely get off of fossil fuels by the end of the century. The people who study this for a living think that it's possible, although difficult. And some of the models actually suggest that stopping greenhouse gas emissions totally wouldn't be enough, and that we would actually have to pull large amounts of CO2 out of the atmosphere. They call it carbon dioxide removal. It sounds great, but the problem is we really don't know how to do that on a very large scale. It's an unsolved problem. Okay, this is actually interesting. Whoops. This is, if I can hold this one here, this is just showing trends in greenhouse gas emissions by country groupings. And the message here, and these are basically emissions, global greenhouse gas emissions from rich countries, from so-called upper middle income countries and poorer countries. The message here is that the emissions from the richest countries are not increasing very much, but the huge growth has been from the so-called upper middle income countries, which includes China. And this is actually a very controversial slide. I'll explain that in a moment. But the reason is that in the international climate negotiations, the dynamic traditionally has been that the developing countries complain that, oh, you rich guys are responsible for producing most of the climate change, for producing most of the greenhouse gas emissions, and we suffer most of the harm. And there's truth to that argument. But what this is showing is that it's rapidly changing, okay, that the developing countries are emitting more and more, and in fact now 2 of the 3 biggest emitters are developing countries, and that's China and India, and the third is actually the US, and we're the second biggest emitter, okay? And as I said, this was very controversial, and this slide was not included in the IPCC summary document because this is one of the things that we could not agree on, and as I said, the way the process works, if one party objects, things are not included. So this slide actually was not included. And we had this 4-day-long food fight about this, which took place in Berlin, and there happens to be a sculpture there called Politicians Discussing Global Warming, and I felt like I was one of these guys here over the course of that discussion. So let me talk now about cost of climate change, and I have 2 simple messages here, and one is this, and one is that a lot of conversations about costs of climate change focus on only one component of cost, and that is what we call mitigation costs. And people, and especially the climate change deniers say, oh, we can't afford to do anything about this problem. It's too expensive, it'll bankrupt the country, okay? And what they're talking about is mitigation costs, and that means costs to essentially shift away from fossil fuels towards a renewable energy infrastructure. And one of the things I want to impress upon you is that's only part of the equation, okay? That's the cost of addressing climate change, but it's also important to talk about the cost of not addressing climate change, okay? That has economic costs as well. Those economic costs can be broken down into two categories. One is what we call impacts costs, okay? And so if climate change causes more extreme heat, as I illustrated, if it causes more wildfire, those things have financial costs. Those are called impacts costs. The other category of costs associated with climate change is what we call adaptation costs, and these are costs of measures that we take to not to reduce climate change itself, but to reduce harm from climate change. So if we expect more wildfire, we might take measures to prepare ourselves for more wildfire, and those measures cost money. Similarly, if we expect more storm surge, we might take measures to protect ourselves against storm surge. Those measures cost money. Those are examples of adaptation costs. So if we talk about climate change, we should really talk about costs in all three categories. And I think in principle, you can say that the ideal climate policy is one that would minimize the sum total of all these three costs. I mean, that sounds nice. The problem is that, first of all, we don't have a clue what those costs are. And secondly, even if we did, the minimization is a tricky problem because to a large extent, climate change mitigation means paying money now to reduce harm in the future, and in some cases very far in the future. And so how do you balance that? No one can agree how to do that. So this is the IPCC's statement about its own estimates of climate change impacts. I'm going to read this to you. So this is climate cost of impacts, not total cost. It says it says the impacts are the estimates of impacts costs are incomplete, depend on large number of assumptions, many of which are disputable. Many estimates do not account for catastrophic changes, tipping points, and many other factors. Okay, so this is saying really we don't have a clue. Okay, but part of the reason I'm showing this to you is it's a window into the frankness of the IPCC about its own limitations. And the IPCC is written by academics, by scientific people, and like scientists typically are, they're very open about what they understand and what they don't understand. But what does the community think that it would cost? And I'm talking now just about mitigation costs. What does the community think it would cost to meet this so-called 2-degree target? And this is how they express it. The cumulative cost, that is the cost between now and 2100 to meet, again, this 2-degree target, would be about 5% of global consumption. And that sounds like a lot, right? Because 5% hit on consumption sounds like a big recession, right? But remember that that's relative to scenarios in which the economy is projected to grow anywhere between 300% and 900%. Okay, so just as an example, if without mitigation, the economy were projected to grow by 500%, which is sort of a mid-range estimate between now and 2100. With very, very aggressive mitigation, that growth would be limited to 495%. So that doesn't sound so bad, okay, even though it's a 5% loss in consumption, okay? And I want to show you this, and this is part of why I don't put much stock in any of these estimates, okay? And this is a humble lesson from the land of refrigerators, okay? And this shows what happened to refrigerator costs, refrigerator prices, when the energy consumption of refrigerators was regulated, okay? And this flies in the face of the traditional mythology that regulation costs money. And so what's going on here? So the red curve is just the size of refrigerators over time, and you can see this goes back to 1947. I don't know if you can read that, but refrigerators have gotten bigger over time, and that growth has sort of slowed down and largely stopped. The blue curve is the price of refrigerators, okay? And you can see that went up, 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 and then started going down, 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 down. And what happened right before it started to go down, 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 down was that the state of California started to regulate the energy consumption in refrigerators, okay? And you can see this is, in fact, the energy consumption in the average refrigerator. And in fact, the state regulated it, the federal government regulated it later, and the energy consumption went down. But what's interesting that the price of refrigerators also went down, even as the energy consumption went down, and the size continued to go up. So it seemed like it was a win-win-win. And what's going on here, and I think what was going on here is that up until this point, no one had really looked at the design of refrigerators in a long time because they were making refrigerators and they were making money, life was good, why should we worry about it? And when the regulations were implemented, I think the engineers took a new look at how to do refrigerators, and they realized that, gee, we know how to do this better. And so I think this was a case where the design of the system was not really optimum, and regulation actually spurred innovation. And I think that this is probably not an isolated example. So I think that the lesson from this is that if we put our minds to addressing climate change, we can probably do it a lot better and a lot more cheaply than we think. I'm going to skip this slide because I don't want to keep it here too long. Okay, so I now want to turn to the famous question, is climate science necessary? Okay, so how does this question come up? This question comes up in the following way, and as I said, people who I really respect make this argument, and the argument is this: look, you folks have done a great job. You've proven that climate change is happening. You've proven that humans are causing it. You've proven that it's bad. Now we know what we need to do. We need to reduce global greenhouse gas emissions, and I've already said that. And in fact, we not only know that, we know that we need to do it a lot faster than we're already doing it. So we don't need any more science. What we need is engineering to tell us how to shift away from fossil fuels and move over to renewable energy. Okay, so that's the argument. So what's wrong with that argument? There's two things wrong with it. Okay, one thing is that we really don't have a good answer to this question: how much climate change is okay? Okay, I've talked about this target, which is widely used in policy circles, of limiting global warming to 2 degrees Celsius. I'll tell you a secret about that. It's actually not based on very much science. Okay, and the fact that that target has been around for 20 or 25 years pretty much guarantees that it's not based on very much science, because the science was pretty immature back then. Okay, so it's a real important question. Is that the right target? And one of the ways in which this question comes up is this issue of thresholds and tipping points, and I'm just going to show you one, and this is Arctic permafrost. And Arctic permafrost is scary stuff. Okay, why is Arctic permafrost scary? It's scary because Arctic permafrost, we think, holds about twice as much carbon as the atmosphere does. Okay, a lot of carbon. Permafrost, the name permafrost suggests permanently frozen. I wish it were. The problem is it's not anymore permanently frozen. It's starting to thaw, and when it thaws, it releases either carbon dioxide or methane. Carbon dioxide is a greenhouse gas. Methane is a much worse greenhouse gas. And so what happens is you can get into this self-reinforcing cycle where warming causes thawing permafrost, that releases greenhouse gases, that causes more warming, that causes more blah, 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 and so on and so on. And the fact that there's so much carbon stored in the permafrost means that this could be a huge amplification factor on climate change. And by the way, this is not included in the models. And it's not included in the models not because we don't think it's important. We know it's important, but we don't understand the science well enough to put it in the models. Okay, so what's the policy implication of this? The policy implication is that we really need to know at what level of warming this self-reinforcing cycle starts to occur. Okay, and maybe that's 2 degrees, maybe it's 2.5, maybe it's 1.5, but we don't know. We really don't have a clue. And the potential consequences are really calamitous, okay? So this is one example of why we need climate science. We need climate science because we need to understand where these thresholds and tipping points are in the system. And it's really shocking how bad our understanding is of some of this really important science, okay? The other reason which I'm going to discuss for a few minutes, is the other reason we need climate science is adaptation, okay? What does adaptation mean? Adaptation essentially means anticipating and preparing for future climate, okay? So I said a moment ago, if we anticipate more storm surge, then we want to take measures to prepare for that, okay? And that requires a lot of knowledge of climate change, detailed knowledge of extremes in sea level, for example, on a very, very local scale. And that sort of knowledge is very difficult to produce, and we certainly need climate science to do that. This is kind of, as I say, state-of-the-art climate decision support. And I'm going to just spend a couple of minutes talking about the intellectual challenges associated with doing climate change adaptation. And what kind of information do decision makers need to know? Decision makers need to know information on local scales. Okay, adaptation decisions are made typically by, say, city managers, so they want to know what's happening in their city, or adaptation decisions may be made by water agencies, so they want to know what's happening in their water agency, in their watershed. So from the point of view of global climate models, these are very, very local scales. Adaptation also depends a lot on extreme weather, because often what causes impact is not changes in average climate conditions, but extreme weather events. And so decision makers want to know about extreme weather events. And I'm getting ahead of myself. Decision makers also want to know about uncertainty. Okay, so the three things that decision makers always ask us for, and by us I mean climate modelers, they want to know information on a very local scale. They want to know information typically about extremes, and they want to know about uncertainty. I mean, in fact, that's usually the first thing they ask is, how reliable is this information that you're telling me? Okay. It turns out that from the point of view of climate modeling, these are all things that we're really, really bad at, okay? These are all really conspicuous areas of weakness in global climate models. And you may ask yourself, how can that be? How can it be that the models are really bad at providing exactly the information that everybody wants to know? And the answer is that climate models weren't designed to inform real-world decisions. Climate models are research tools, okay? That's what they were, that's what they are. They were designed to help for people who want to study climate processes. They were not designed to inform this kind of decision. And I'll tell a little story about how I got into doing climate modeling for decision support. And this was back in around 2001. I was working at Livermore Lab, and they purchased this computer, which was called ASCII White. It was literally the fastest machine in the world at the time. I think it cost $100 million. And it had a small army of people 24/7 keeping it going. And while this thing was being debugged, they let me use it, okay? So I had the opportunity to use what was then the fastest computer in the world for some unknown period of time. And by definition, it wasn't working right. And I knew that as soon as it started to work right, they were going to take it away. Okay, but I didn't know when that was going to be. And what I decided to do with it is me and a couple other guys decided that we were going to take the climate model of the day and just crank the spatial resolution down as fine as we could and see what happens, okay? And when we talked to the purists about this, the people who developed the model, they were horrified. And of course, that just increased my glee at trying to do this. And what they said is, you can't do that. The model isn't designed to run at that resolution. It probably won't work. It's just going to break, okay? And it turns out actually that they were right. It didn't work at all. And it took us 6 months before we stopped getting garbage. But ultimately, we got very nice results out of it. I'm going to show you what it looks. Oh, before I do that, I'm going to show you this. This thing, it looks like a garbage can, okay, but it's not. What it is, it's the latest Apple desktop computer. And the point of showing this is that this machine, which you can buy for $4,000 now, is about 70% as fast as this thing, which you can see it's as big as a house, and I think it literally costs $100 million. So computing gets better. So this is I'm just going to illustrate what a fine resolution model looks like. This is actually not a fine resolution model. This is the coarse model, and what you're seeing is in these clunky squares is that this model is calculating things averaged over each of these squares, and this is still a pretty state-of-the-art global climate model resolution, and that's why these models aren't good at informing real-world. That's one of the reasons why they're not good at informing real-world decisions. Okay, because if you care about Hetch Hetchy watershed, you can't get reliable information about Hetch Hetchy watershed out of that model. Okay, it's simply too coarse. Okay, so this is what the model looked like when we cranked the resolution up to about 50 kilometers. Okay, it looks a lot more like planet Earth. Okay, and you can actually see this is February, so you can see exotropical cyclones forming in the Gulf of Alaska, and rain bands hitting. You can see also it rains at the same time every day in the Amazon. Okay, so it looks a lot more like planet Earth. We did also a lot of quantitative. Oh, I was going to mention hurricanes. So one of the first things, I was really excited about the possibility of having hurricanes in the global climate model, because this kind of model, as you might imagine, there's no hurricanes, right? And it's a really interesting question. What happens to hurricanes with climate change? So when we ran this model, one of the first things I did is I was like, are there hurricanes? Actually, there weren't. But we subsequently developed another version of the model. We changed some of the physics that did have hurricanes. Unfortunately, somewhere along the line I lost this animation, but I think you can see that these little cyclonic sort of objects. This model actually was too good at producing hurricanes. Anyway, I showed you anecdotally that model looks more like planet Earth. We did a lot of quantitative analysis, which actually demonstrated that it not only looked more like planet Earth, actually, in fact, was more like planet Earth. I'm not going to go through that because I don't want to keep you here all day. I do want to mention one more topic about informing real-world decisions, then that has to do with uncertainty in future climate. Okay, and when you talk to decision makers, some of them have this naive notion that if we just wait a few years, that the scientific community is going to reduce uncertainty, and then we'll have perfect information on how wonderful life will be. Okay, and you try to explain to them, well, that's not really how science works. We're never going to give you certainty. Okay, and so non-scientists talk about reducing uncertainty. Scientists, we talk some about reducing uncertainty, but we would be happy just to be able to measure it, and that is difficult enough. Okay, and my message is don't expect either of these things to happen soon. So why am I pessimistic about that? I'm pessimistic about that, well, for reasons that are not very sophisticated, but let's just talk for a second about where does uncertainty in future climate come from. One, especially if you look farther into the future, one big source of uncertainty in future climate is what I call drivers of future climate, that is greenhouse gas emissions. Okay, so future climate depends on how much fossil fuel humanity uses. It depends on decisions made by you and me. It depends on decisions made by the state of California. It depends on decisions made internationally. So, and that's a big source of uncertainty, right? And that's not a science problem, right? No amount of scientific study is ever going to tell you future human use of greenhouse gases, right? So it can't. This is an uncertainty that can't be reduced by any amount of scientific research. Okay, so you just have to make assumptions about future human use of greenhouse gas emissions and then move on. So I say these are inherently unknowable. The other source of uncertainty really is a true scientific uncertainty, which is this, and that is that even if we knew perfectly well how many greenhouse gases humanity is going to use from now into perpetuity, we do not understand perfectly how the system responds to those greenhouse gas emissions. That's a true scientific uncertainty. Further study will reduce that, but as you know, science marches on, but it marches on only slowly. Okay, and the idea that we should postpone making decisions about climate change until we have better information is not a good idea, because there's a lot of urgency about addressing this problem, and as I said, the progress of science is way too slow. I'll just mention a word or so about some of the institutional challenges of doing climate change adaptation, because that's something I'm interested in. I think it's tremendously difficult. I think it's tremendously interesting. It's often something, though, that academic institutions have difficulty doing well, because the truth is a lot of it is it's very, very applied. Okay, a lot of I think of climate change adaptation as essentially applying existing knowledge rather than generating new knowledge. This is not something that universities are necessarily good at rewarding. Also, to really do this well, you have to work a lot with the decision maker and understand their system. And I used to do that. I spent a lot of time working with water agencies in the state of California, for example. And you have to spend a lot of time understanding their system and holding their hand. And I found it very interesting, but not everybody does. And the other thing that you run into is that decision makers who are affected by climate change have some of them have very sophisticated understanding of things, others don't. Okay, water agencies, for example, are super sophisticated in how they understand weather and climate. They're very used to dealing with probabilistic information. It's easy for us to work with those guys. Some decision makers, as I said, they just want answers, okay, and they're disappointed that, oh, you mean you don't have answers? No, okay. All right, so I'm almost done. I do want to mention a few things about recommendations, and I'll start with priorities for policy and for research, and I'm afraid there's nothing very original here. I will mention that I think one of the things that the United States government, well, a lot of the things that the United States government has done recently are great, and this is perhaps the best of all, and you probably heard this in the news. This was last November. There was a joint announcement between the US and China, and both countries announced pledges for reducing greenhouse gas emissions, and these are very, very, very substantive pledges. We announced that we would reduce greenhouse gas emissions by 26 to 28% within the next 10 years, and China announced that they would, their emissions would peak by 2030 or sooner. And these are not only very, very substantive targets, but I think this is potentially well, there's a couple of things that are significant about this. First of all, notice that this is it's not even really an agreement because these targets were determined independently, okay? But this is changing the model of getting 195 countries to agree and getting 195 countries all to make identical pledges. So this is, the two biggest emitters got together, we each decided what we could do, and we made a joint announcement, okay? And you notice that their target is very different from ours. It's not only the numbers are different, but the form of the target is different. But it's great, right? And the two biggest emitters made very, very substantive announcements. And as I said, these targets are significant. And the other thing that's important about this joint announcement for us is that, you know, for decades in the climate change policy world, the U.S. was the bad guy, right? We were the biggest emitter. We weren't doing anything about it. And both of those facts are no longer true. We're no longer the biggest emitter, and now we're really starting to take very significant action. And what this does is it gives us moral authority. It gives us moral authority to go bludgeon other people and get them to act as well. And I can tell you that the other big emitters, in particular India, really is feeling the pressure now that they need to get on board and make substantive reductions as well. So I think these are great. Unfortunately, these pledges only go through 2025 or 2030, so we need more. I have to tell you, this is not an original recommendation, but I am one of the people who thinks that we should have a carbon tax. You can ask me about this if you want in the question and answer, but I like carbon tax a lot better than cap and trade. Cap and trade is just too messy. One of my pet interests is investing in the electricity grid. Having a better grid would make it a lot easier to adopt weather-dependent renewables on a very, very big scale. You know, in terms of research priorities, you know, and this is something I worked on a lot in Washington, and it made, I would say, incremental progress with me and a few other people. But, you know, to me, it's insane that, you know, Arctic permafrost is this huge threat, and it should be a gigantic international research priority, and it's not. And to me, the only thing that makes sense in terms of research priorities is let's focus on the big threats. Okay, what are the things that are really threatening to humanity? And the phrase we use is thresholds, extremes, thresholds, and tipping points. That is, extreme weather thresholds like at what point do we commit to the eventual complete melting of the Greenland Ice Sheet? That's a big problem down the road. And tipping points, I mentioned repeatedly. The example of Arctic permafrost. We need to understand these things a lot better because these are the things that are really dangerous. Okay, so why are we not focusing our research dollars on those? It seems nutty to me. I think there's a lot that could be done on the economics of climate change because, as we all know, especially in the United States of America, money drives everything, right? And actually, in closing, I'm going to give you some reasons for optimism, reasons for pessimism. I'll start with pessimism, but I'll get back to the economics aspect. As I say, climate change continues. I mentioned climate change. 2014 was the warmest year on record. There are connections between climate change and extreme weather, which are scary. I've mentioned tipping points a couple of times. The other thing I would say that from the perspective of someone who's been looking at this problem for 20 or 25 years, the more we learn, the scarier it seems, okay? That's my impression from, as I said, 20 or 25 years of looking at this problem. The 2-degree goal, if it is the right goal, it's going to be tough to meet. You know, it's true that the public gets it about climate change more than people think, but it's also true that climate change is not a high priority with the public. They don't have the sense of urgency that I think they should have. And as you may know, there's a very, very well-funded climate change denier industry, which actually does a very great job not only of promoting its messages, but of covering its own tracks. And the other thing that I would say is pessimistic is that with the results of the latest election, prospects for research funding, you know, who knows? It doesn't look great. On the other hand, you know, there's reasons to feel optimistic. You know, as I mentioned, the government, especially in the last 4 years, is really doing a lot. They're really doing substantive things, and they're doing things that will be difficult to reverse. And I'll mention here the EPA regulation of greenhouse gas emissions under the Clean Air Act. And this has been a long time in the making, but the legal foundation of that is really rock solid. I mean, it's been through the courts, it's been challenged, it's been upheld. I don't see how you're going to undo that, okay? The federal government has really done a lot about implementing adaptation, And I mentioned already the joint announcement with China. I think these things are great. The other thing that I really see happening that's very encouraging is that the business community is starting to take climate change a lot more seriously. I think they see it as both a threat and an opportunity. And I think that that's really, really powerful. And as I said, in the long run, the policies in this country tend to be driven, I think, more than they should by folks who have money. And as the business community gets it more and more about climate change, I think we'll see more and more action. Okay, so I'm sorry that I went on and on, but I hope you found that interesting. Thanks very much. Thanks for coming.
First, but you're next.
Just a quick question about your last slide there. I read the newspaper. The Pentagon a couple of years ago said this is a security threat, and so that sounds kind of an important statement. Is that of minor importance, or is that a big deal in Washington?
I think it's a middling. The climate. Not only the military, but also the intelligence communities are really concerned about climate change. The intelligence communities, well, both of those communities see it as a source of social unrest and conflict, and they're concerned about that. And the military is concerned about it. What they're concerned about, which is their warfighting capability. The Navy has something called Task Force Climate Change. And if you quiz them, the thing that they're really worried about is the Arctic Ocean, and the fact that the Arctic Ocean is now navigable, or shortly will be navigable, and they want to be able to fight battles in the Arctic Ocean, and right now they don't feel like they can do that. They don't have the ability to project force. The Navy has literally no icebreakers, for example, and so it's something they're concerned about. Yeah, so they're concerned about climate change, not necessarily for the right reasons, but or what I would consider to be the right reasons.
My name is Otto Robbie. I'm a retired professor. I'd like to bring up two issues and see what your comment is on them. The Danish Meteorological Institute has been studying the temperature versus solar sunspots. They've found a very precise relationship. It doesn't involve carbon dioxide. It's very precise, over 70 years.
Right.
And that makes me think that perhaps the sun is most important part of it. Okay.
You're not going to like my answer. Okay.
You have to look at their data.
I've looked at it. I know. I've seen it. Okay. Yeah. Well, no, look. The greenhouse effect and as a phenomenon has been understood for a couple hundred years. The fact that there's a greenhouse effect in the atmosphere has been understood for over 100 years, and there's published papers about the effect of carbon dioxide on temperatures on the ground that I can show you that were published in the late 1800s. The idea that the sun is causing global warming, I would characterize as a non-solution to a non-problem. Okay, and it's a non-solution in the sense that the energy output of the sun has been monitored by satellites for 30 years, and it hasn't gone up. Okay, so it doesn't work as an explanation for climate change. And the other thing is that it's a non-problem in the sense that if there were some alternative explanation for the warming of the planet, then that would call into question some very well-established physics of greenhouse gases. And we would have to then explain, well, why is it that we've added all these greenhouse gases to the atmosphere and it hasn't done anything? So I'm sorry, but I just don't like that. I just think it's scientifically, it's wrong.
I have one more issue.
Okay, sure.
That is that we know that 1,000 years ago, the Earth was a lot warmer than it is now. Some very good studies have shown this and have been published. When Eric the Red came to Greenland and set up gardening and vegetable gardens there,
right,
it was much warmer. And there are several studies, published studies, that show that it was much warmer at that time, 900 to 1000 AD.
It was a little warmer, I think. Yeah.
More questions?
Okay, so a couple of questions, but I'll just ask one right now. And it's related to, you say that we need these policies and we need the governments to enact, but I think we also need a lot of personal and social buy-in. And you have people that just don't believe that this is a problem, for one, and they are hard to convince. And you have people who think it's a problem but are unwilling to change.
Right.
And you have people who think it's a problem and are currently doing things. So my question is, how do you address the people who know it's a problem, think it's a problem, acknowledge it, but are unwilling to change their behaviors on a personal level?
Okay, that's a really good question. I would say, for one thing, you know, I think it's important not to make people, not to blame people for climate change, or not to make them feel blamed. And you know, we all live in the context of our times, and you know, our own impact on the planet and our own consumption of greenhouse gases is really determined to a large extent by the societal context in which we live. And I'll just give you an example. You know, I spent most of my life here in California, and when I'm here in California, you know, I drive as much as anybody does. And I produce my share of greenhouse gases. I also spent 3 years in Washington, D.C., and I never drive in Washington. And why is that? Because there's a metro, right? So it's an example of, you know, I live in the context of my times, and if you give me an option that's more environmentally friendly and is reasonably convenient and reasonably inexpensive, I will gladly take it, okay? So that's one point. I would say the other thing about social change is, and this is one of the things I learned in the NGO world, is that you can sample public opinion and subdivide public opinion, but I think history has shown that social change is brought about by actually a small subset of the population who really, really care about an issue. And the social scientists have a phrase for this, which is called the issue public, okay? And these are the folks who care enough about a given issue to go out and agitate for it. And I mean, you can think of all kinds of examples of different issues where there's a small segment of the public who is really passionate about an issue, and they actually end up determining policy. And that's not always a good thing, right? I mean, there's plenty of examples where we have policies in this country which the majority of people oppose, but you know, a vocal and well-funded minority you know, manages to push through policies anyway. And you know, I think what we need on climate change is we need an issue public, and you know, I think we'll get one. So I'm responding to your question about how do we address the sort of middle ground of people, you know, the 60 or 80% who believe it's real, but you know, hey, I'm busy, you know, I just don't have time to, you know. And my answer is, I don't think you necessarily need to. I mean, I think those are the people who will willingly be led. I think what you need to do is inform and agitate the issue public, and that's how change happens.
Hi, my name is Mike Russell. I'm retired from the university. Recently, the oil companies on their webpage, Shell, Exxon, BP, et cetera, have all acknowledged climate change.
Right.
In April, the Koch brothers both independently acknowledged climate change.
Right.
Is there any evidence that the White House, or is there going to be a push between now and December?
Be a what?
To make something happen with the Republican Party, basically? You
know, okay, I could say this about that. I mean, I hadn't heard that the Koch brothers have acknowledged climate change, but you know, I know that they're if they're doing that, they're at the same time very actively funding the denier industry. And they do that, and they not only do it, but they try to obscure the fact that they're doing it. And the same is true to some extent, I think, of the bigger fossil fuel companies as well. They funnel a lot of money through these shell organizations that have innocuous sounding names, and the purpose of that seems to me to be to just kind of you know, cover their tracks and cover the money trail. As far as Republicans go, you know, I had dinner about a month ago with a guy named Sheldon Whitehouse, who's a senator from Rhode Island, and you know, he is convinced, and he would know better than I, that the Republicans, or a big segment of the Republican Party, wants to shift its position on climate change, that they're sorry that they've sort of painted themselves into a corner in the sense that they've ridiculed the issue. And you know, what they're looking for is a face-saving way to change their position. And I don't know how you give that to them. Maybe the way you give that to them is you talk about you know, if we shift away from coal, you know, the public health benefits of moving away from coal or something like that. I don't know. So I don't know. I don't have the answer.
You mentioned permafrost as a tipping point, and I wonder if there's other tipping points
Sure.
that you're particularly concerned about.
Well, yes, and the major land ice sheets are probably the best examples, right? And the issue with the major land ice sheets, and the two major land ice sheets, there's Greenland, there's Antarctica. Okay, Greenland is actually by far the smaller one, but the issue is that at some, and I didn't show you this slide, but at some point the melting, well, it takes a long time. It'll take centuries for those ice sheets to completely melt. Okay, but the tipping point is that at some point that becomes inevitable. Okay, and maybe it takes 400 years for that process to play out, but at some point it becomes unstoppable. Okay. And the other thing that's interesting, and I do have a slide about this, although I buried it because I didn't want to keep it here. Oh yeah, this one. Okay. The other thing that's interesting about Greenland, okay, and is that this is truly a tipping point in the sense that the melting is, in one sense, is self-reinforcing, and here's how that works. Okay. And what this is showing, these are measurements of the reflectivity of the surface of Greenland, okay? And what this is showing is that the surface has gotten darker over time. And why has it gotten darker? It's gotten darker because the periodic melting and refreezing, which is new, which we're now experiencing because it's warmer, changes the crystal structure of the ice, and it makes it darker. And of course, when it's darker, it absorbs more sunlight, and that reinforces the warming and so on. So this is another tipping point. And as far as Antarctica goes, there was a paper about a year ago showing that part of the Antarctic ice sheet, a small part, apparently has passed a tipping point, and they now think will melt completely. And I think they said well, they don't know how long it'll take. It'll take 300 or 400 years, but it's literally unstoppable. You know, it's going to happen. And so that's a case where we apparently crossed a tipping point some time ago, and only after the fact did we realize it. And that's not a good way to run a planet.
So California has a history of being out ahead on environmental issues, maybe ahead of the federal government. And you know, California is very active in terms of climate policy and energy policy related to climate policy. So I'm interested in your perspective from your time at the White House about how this is viewed. I mean, is this viewed as productive and constructive in that,
it's great.
Or a distraction?
No, it's terrific. We love it. In fact, we had, one of the things that over the last year I was there, we actually had weekly conference calls with people in the state of California, just because we were trying to implement some adaptation policies at the federal level, and we recognized that, gee, the folks in California have been doing this for some time, and there's a lot that they can teach us. And so we actually actively worked with folks in different agencies in the California government, including the governor's office, but the agencies that you know and love very well. So no, we think it's great. We love it.
Thank you very much. I was wondering if the response of climate is similar all over the world to the carbon emission reduction. In other words, are there any priority or difference in the effect that you may say these parts of the world are more efficient if they reduce the gas, CO2 gas emissions?
I'm not sure I understand your question.
You didn't understand?
No, I'm not sure. Sorry. Maybe can you repeat the question?
I mean, considering the circulation model, okay, general circulation models, are all parts of the globe have the similar effects on the climate?
Are you talking about impacts of climate change?
Impacts, yes.
Oh, yeah, okay, sorry, okay. No, the impacts really vary, right? And, for example, I talked about water scarcity in California, right? And how that's driven by loss of snow. Well, that's an example of an impact. That occurs where you have snow-dominated hydrology, Western U.S., the Himalayas. But, in many parts of the world, that's simply not an issue. I mentioned storm surge, right? Obviously, that's, depending where you live, that's either a big issue or a non-issue. So, yeah, no, impacts are very highly, regionally dependent. And that's one of the reasons why climate change adaptation is difficult, because, the impacts vary so much from region to region. And, to do adaptation well, you have to understand, the impacts on, in every region. Okay.
And then we're going to have refreshments, and if there are more questions, we can just talk before during the break.
Hi, Rob Beggs, College of Engineering alumnus. Thank you again for your presentation.
Oh, sure.
Question, the melting of the Antarctic and Greenland ice seems intuitively that it would be very non-linear. I mean, in other words, as the sea level goes up, it will unground more ice more rapidly, and it's just kind of a positive reinforcing. Is that captured in the IPCC modeling of sea level rise?
Yes, good question. I'm actually not sure of the answer, to be honest with you. I don't know, because that's called the ice sheet dynamics, and that's I think it's captured very primitively, and the IPCC estimates sea level rise in a kind of a clunky way. They estimate the different terms independently. They estimate thermal expansion term and the straightforward melting term, and then they have the ice sheet dynamics term, which is what you're referring to, which is by far the most uncertain term. And it's done in a very kind of ad hoc way. That is, you put your finger on, I think, the biggest uncertainty in future sea level rise. And if you compare IPCC's estimates of sea level rise, the most recent ones, to the ones that they issued 7 years earlier, the most recent ones are much higher, and that's largely because of improved understanding of the ice sheet dynamics phenomenon. My personal opinion is that the estimates are still overly, they're still too low. And a lot of other folks think that as well, but who the hell knows, really, right?
Yeah, Christine Shoemaker, I have a question relating to your preference of the carbon tax over the cap and trade.
Oh, yeah.
Relating to the question then about what you thought perhaps various different parties in the government would be willing to go for, and feeling that they were backed into a corner. There is sort of the idea of a revenue neutral carbon fee.
Right.
Is that something you think some of the people who feel backed into a corner would be able to support?
I do, and I know that I've had conversations with a few of them, and yes, I do think so, and it's a hard, well, I think it's a relatively easy thing to support politically, right? Because if it's revenue neutral, what's wrong with that? In that sense, it's not a tax increase, and yet you can argue that, look, instead of taxing income, which is something we want to encourage making money, right? Instead of taxing income, we'll tax pollution, right? Which is something we want to discourage. I mean, it makes a lot of sense. My dislike of cap and trade is that, in principle, it seems like this really simple, really cool market-driven system, but if you actually look under the hood and look at the details of it, it gets really messy, especially if you start talking about offsets, and in those markets that have offsets, you get armies and armies of lawyers involved, and right away I get worried about that. Why are there armies of lawyers involved here? That doesn't seem good, And what I worry about is that, there's opportunities to game the system, and that there's opportunities for fictitious, and I know, in fact, there's opportunities for fictitious emissions reductions. And I think the nice thing about a carbon tax is, it shuts all that stuff down. It's much simpler. You just, you emit, you pay. It's pretty straightforward, or it's much more straightforward anyway.
I had a question about, there was The Guardian had an article about blobs of warm water off the coast of California.
Oh, yeah.
And I wondered what you thought about that, and are there any other coastlines around the world that show similar patterns?
Mm-hmm. And the article about the blobs of warm water was in the
they were talking about unusual warming around the California coastline.
Was that in the context of the drought?
They were talking about the drought.
Yeah. Well, what do I think about that? I think that there's no question that the proximate cause of the recent drought has been this very unusual and very persistent meteorological pattern, this high pressure system, in the Gulf of Alaska, which is, that's the normal thing to have in summertime, and that's why we have the summertime dry season, right? That's supposed to go away in winter. It's oversimplifying slightly, but basically it hasn't gone away in winter, okay, over the last several years, and that's related to this glob of warm water. And there's been some work at Stanford University, two guys named Daniel Swain and Noah Diffenbaugh, who have, I think, argued pretty persuasively or done some model simulations that show that that bizarre meteorological pattern that's responsible for the drought is made more likely by climate change. Does that happen in other places? Yes, but the example that I was thinking of is not coming to mind right now. But actually, Brazil, they had a similar drought. I don't know if that's been associated with climate change, but they had a similar drought with a similar phenomenon of a very persistent high-pressure system, which didn't actually reduce precipitation, but it just diverted it away from where it normally would fall. And that's exactly what's happened in California. The high-pressure system has diverted the rainfall away from the state of California.
So let's thank Phil one more time. And those doors to your right are opening to let you out and have food and drink.